Hey, all you Greta's and Shootas cats out there. Welcome to Environmental Science Notes, Chapter 5, Section 3, What Limits the Growth of Populations? So, populations cannot grow indefinitely due to limitation of resources and competition among species for those resources. So we can't just grow forever, whether it's human population, bug, bacteria, whatever. You always have limits. So, you got three options. Population as a group of a population, let's start over, is a group of interbreeding individuals of the same species that usually live together in the same geographic area. So you're looking at the same species, but a whole bunch of them. That's a population. So we can change on a couple things. It can get larger if more babies are born. It can get smaller if a bunch of organisms die. Immigration is into. I for immigration, I for into. So this is the arrival of individuals from outside the population coming in. Emigration, so that's going to make the population larger. Emigration, E for emigration, E for exit. This is the departure of individuals from the population. So maybe something is happening and they've decided to leave, and that's going to make the population in that area smaller. You can also maybe have a whole lot of births, so that will increase, but then you have a whole bunch of people leaving, so that will decrease. So these things can cancel each other out, but understand that births and immigration are going to increase a population, whereas deaths and emigration are going to decrease a population. So you can also look at the age structure and how that affects the population size. So the age structure is the distribution of individuals among various age groups. So you can look at pre-reproductive, so before puberty, reproductive, which is going to be puberty through menopause, and then post-reproductive, and that's after menopause, which biologically speaking, you're not really helping anymore. And this affects how rapidly a population grows or declines. So if most of your population is in pre-reproductive or reproductive age, you're going to have a very quickly growing population. But if most of your population is post-reproductive, it's going to be a very slowly or declining population because nobody's making babies. So we got a couple of factors that can limit population size. Each population in the ecosystem has a range of tolerance, what makes it happy. So its ability to survive under various physical and chemical environmental conditions. So polar bears like it cold. A lizard might like it really warm because they live in the desert. An amphibian is going to like it wet because those are their environmental conditions. Fireflies like to come out at night, or lightning bugs, whatever you call them. Some individuals in a population may also have different ranges of tolerance for temperature or other physical or chemical factors due to differences in genetic makeup, health, or age. So you're always going to have some variety, but you'll still have your range of tolerance that works. Then you get a little bit out of your range of tolerance, but if you get too far out, then you die. So here we go. Optimal range, this is your abundance of organisms. The zone of physiological stress has a few organisms. Maybe it's a little too hot or a little too cold. A couple things can make it. But if it gets too hot or too cold, nothing is going to live. So this is one example of a range of tolerance where most of the things are in the middle with a few on the outside of the curve. So limiting factors limit the size of a population. So on land, precipitation is often a limiting factor. How much rain an area gets, because that's going to control how much plants are in the area, which will control everything else in a food web. In aquatic ecosystems, you can have tons of different limiting factors. Temperature, how deep the water is, how clear the water is, which will allow for more or less sunlight. The availability of nutrients, how acidic it is, how salinity it is, which is how salty it is, or the level of oxygen in the water. Can't breathe, can't live. An excess of a limiting factor can itself be limiting. Water, good. Too much water, bad. If your land is flooded, it's hard to do much on it. Water, too much acidity in aquatic environments will often damage that, which we'll be talking about later this year. You can have what are called density-dependent or density-independent limiting factors. So population density on itself is the number of individuals in a given geographic area. So how many of whatever are in this space. So density-dependent factors become more important as the population size increases. So parasites and disease spread more easily. Think about how quickly COVID went through New York City before people learned about social distancing, because everyone is really, really close to each other. So the more dense the area is, the more quicker stuff is going to pass. The less dense population-wise an area is, the less quickly these things are going to affect them. Sexually reproducing individuals can find mates much more easily. Think, once again, big city versus a small town. But this works for all critters as well. And then you have your density independent factors. And these are things like drought and climate, different weather-related events. Tornado is going to happen whether it happens to a city or one person. If it rains, it's not going to like follow you home from school. It's just going to rain on everybody or one person if that's all that's there. So density independent factors don't care. It'll rain on New York City. It will rain on Boise, Idaho. It will just happen. So density dependent, more important as the population size increases, and density independent doesn't matter. So if it can happen in New York City and Boise, Idaho the same, probably density independent. If the chances of it happening in New York City are way more than Boise, Idaho, then it's probably density dependent. Now, there's something called exponential growth, and some species reproduce and grow exponentially. And this will be shown in what's called a J-curve, which is coming up on another slide or two. So these members reproduce at a very early age, many offspring in each generation, and the time between generations is short. Some bacteria literally reproduce every 20 minutes. So that would be a great example of something that grows exponentially. Now, all species have some type of growth limits, whether it's they need sun, they need water, they need temperature, they need space, nutrients, predators, disease. Something is going to limit their population. Once again, no population can grow forever. You always have some type of environmental resistance. So the sum of all factors, so your environmental resistance is the sum of all factors that limit the growth of a population, which also leads into what is called carrying capacity. Carrying capacity is the maximum population of a given species that a habitat can sustain indefinitely. So think of like just your basic fish tank. You can put a couple fish in there and they'll be happy. Probably put a couple more fish in there and they'll be a little stressed, but they'll be okay. But I couldn't dump 100 fish into a fish tank and have them be happy. So that fish tank has a carrying capacity. Every ecosystem has a carrying capacity for what it can support healthily forever. So the maximum population that they can sustain indefinitely. As the population approaches carrying capacity, what starts off as a J curve turns into what is called an S curve. And this is also called logistic growth. And the easy way to remember that is logistic with an S in it makes the S curve. So here is your J curve. Grows really, really fast, and you can make a really large population very quickly. This is not reality. That you will always have some type of limiting factor that will have the population hit carrying capacity. So usually what happens is you have overshoot, and then you have die-off, and then you have overshoot, and then you have die-off. Because the individuals aren't going to know, okay, this is the exact number. So sometimes they make too many babies, and then some will die, and then they have extra stuff, so then they'll make more babies again. So populations kind of have this overshoot and die-off for a while until they reach that happy number. So this is your J curve that looks like a J, and your S curve, which looks like a really funky S, but that is the S curve over there. So understand populations can crash, especially when they massively overshoot that carrying capacity. So once you go over, you have that dieback or that population crash. So it's got three options. It can stabilize the population, it can switch to a new resource, or it can move. Now, we've talked about these things before with other things. So once again, if you're stuck in an area, either figure out a way to make that population work, find new resources, or go somewhere else and use those resources. So here is an example of population crash. This is the number of reindeer in this area. So I don't know what happened here, but you have a massive growth of reindeer way, way, way above the carrying capacity. And then you have this huge crash of reindeer. So Santa definitely had a shortage of reindeer after that. In the 50s, massive reindeer shortage. Talk to your parents, they'll explain it to you. So when you have that exponential growth, I don't know if they got access to like some awesome new whatever, massive overshoot, massive population crash. It's going to happen. And we survived. Once again, notes. So you are done. Before we go, I want to take this opportunity to let you know that you are good enough, you are smart enough, and people do like you. And in case I don't see you later, good afternoon, good evening, and good God, do your homework.